actually, it's kind of interesting what they do. They set up one room for one experiment, and one room for the other experiment, and then we like switch rooms on Tuesday. Just so you're emotionally prepared. Well, yeah, that is kind of, but I just wanted to remind people, because, you know, sure there's a syllabus and sure you can be like,
People don't read it. People don't look at it.
Haven't opened, some people like they don't like book quizzes and stuff on their syllabus and stuff like that, but I'm not sure if it necessarily helps.
It all depends on how well you.
And I get caught by stuff like that too, I mean, yeah. Stuff appears on my calendar and I'm like, oh yeah, there's an all faculty meeting tonight. All right. All right, so again, remember, if you recall, we're in the middle of talking about some of the factors that affect entropy. We've already talked about Coulombic charges, we've talked about phase, what phase something is in, and now we're going to make a generalization, and we're going to say that if you have a solid, okay, if you have a solid, entropy increases very slightly. And it's very interesting, if you don't remember, you'll want to review that if we have a phase change, there is no temperature change during a phase change. So if you have, yesterday when you had your Bunsen burner and you were boiling water, you were actively putting energy into your water. And so what was happening, that energy is used to make the phase change, right? Right. Okay, so there's no temperature change, but you'll notice here, if you look at it, we sort of had this much change in entropy. And we have a much larger change in entropy, and that should make sense, because what happens in the phase change? Our substance goes from being a solid to a liquid. An increase in randomness, an increase in dispersion. Yes?
If we had like perfect control of the temperature and we stopped right on the line, is it possible would it be in between the solid and the liquid? Or
in between the solid and the liquid. So what you're talking about is if you had some type of a thermometer that could read negative 0.00000001 or something, right? Is that what you're trying to say?
well, if you just stop the temperature right on the line between solid and liquid.
Okay, but then you're going to be at, if you're at this temperature, you're at the temperature of the phase change.
Yeah.
So the solid and the liquid are in equilibrium with each other.
Okay.
Okay? All right, same thing happens. When you heat your liquid, you get an increase in entropy. If you recall when you did phase changes before, probably when you did heat, when we go from solid to liquid, we get some more randomness. When we go from liquid to gas, we get tons of increase in randomness. So as we go from a liquid to a gas, there's actually a larger increase in entropy. Our bottom line is that S increases slightly with temperature if you're talking about a particular phase, but S increases a large amount with phase changes. Okay? Alrighty. Now, if we wanted to calculate our change in entropy for a reaction, it's the same type of formula. If we had 2 hydrogen gas, oxygen gas yielding 2 waters. Now the thing to remember, for both free energy and for enthalpy, we would have zeros here, and we would just look at our standard heat of formation for water and multiply by 2, right? But we can't do that here because our hydrogen has a value for hydrogen, and it has a value for oxygen. And you'll notice because I have two reactants and I don't want to forget that this negative distributes here and here, I've put my reactants in brackets. And so I recommend that to you highly. Excuse me. And here we have the relevant calculations. The entropies were consulted in a table. So these numbers, I didn't just pull out of a hat, they were found in a table. And just a word, the table has all the thermodynamic data. So if you have water, it'll be enthalpy, Gibbs free energy, and then entropy. So you find any thermodynamic value in the same table, especially if you're looking in the appendix. If you're looking within the chapter, they'll be in different tables. The enthalpy one will actually be in chapter 6 for this book, and so that's kind of difficult, but it'll probably be given in the problems as well. If we crunch the numbers, our overall change in entropy, our standard change in entropy for this reaction will be a negative 326.9 joule per Kelvin. Now, let's see if we can understand that value and see if that makes sense to us. What did we have? We had 2 moles of gas plus another mole of gas, and they became 2 moles of a liquid. When we go from mainly gases to a liquid, that would overall generally tend to be a decrease in entropy, right? And so the value that we got does pretty generally make sense. All of our standard entropy values were positive, but we got an overall change in entropy for the overall reaction. Yes?
So as far as units go, the change in S is just joules over Kelvin, but then for...
Oh, so I was just talking to somebody, but what did we, so what did we do in this particular, sorry, I cut you off.
No, it's okay.
What did we do? We took this number, we multiplied by 2 moles. So the standard change in entropy for this reaction, right, is this amount, okay? If you were to look at the standard entropy value for water, the standard entropy value for water would only be this 69.9 joules per Kelvin mole, right? So what's the difference between them? In this particular place, we took this value and we multiplied by 2 moles. Does that make sense?
Yeah.
So if you look in a standard table, it'll be joules per Kelvin mole. For a particular reaction, we might have more than 1 mole, and so it may be a change in enthalpy that's just joules per Kelvin. Okay? So there is a decrease in S because 3 moles of gas give 2 moles of liquid. Okay. This is